Hey everyone, this is John Buck back again with this is the third installment on our story about array perturbations, particularly looking at what happens when sensors in the array are perturbed from their nominal position. So if you haven't seen the first two episodes, you want to go get the backstory before this one. But where we got to in the last episode, we said we set up our numerical, our probability model and saying the power pattern for the perturbed thing, that's B tilde, we want to find the expected value of it. On average, how close does it get to the nominal one? And so we had gotten this big expression where all the randomness is in these delta p's. These are the errors in the element positions, and each one of these is a Gaussian with some variance sigma p squared, independent for each of the three dimensions, x, y, and z, in this three-dimensional vector that describes how the sensor has been shifted from its ideal location. So when I take the expected value of this, the w's are all fixed, and these are all deterministic. And so I can bring the expected value inside the sum and inside all the deterministic things and say, well, the only real random thing going on inside this sum is that last exponential. So let me focus my attention there because I need to get the expected value of that. So I want the expected value of e to the minus j k transpose times delta pn minus delta pm. Pn as in Nancy and then Pm as in Mary. Right, this is the only randomness inside this whole thing, so the expected value is going to come down to the expected value of this. And just to sort of give it a name to simplify things, we're going to call this beta sub nm. Right, so this is this expression, or the whole thing including the expectation is the beta. So we say the expected value of this exponential of the perturbed sensor locations we're going to call beta, just sort of as a shorthand, or it's almost like in programming where you break something out as a subroutine and say, let's worry about that one piece, and then we'll fit it back into the bigger overall problem. Okay, so if we're going to find this, we need to simplify things a little bit. We're first of all going to take, it'll be helpful to say, I'm going to take the general 3D wave number, and I'm going to write it as 2 pi over lambda times a unit vector. And I guess technically, to follow Van Treese's notation, this would have a minus, but it won't actually affect our analysis that much in the end, where this u is the unit vector in the k direction. So we're basically separating the directionality from the magnitude, right? The minus 2 pi over lambda, or we'll probably also just write this as k naught, right, is the magnitude of the wave number, and u is the direction. And where that helps us is looking at what's going on. Then we can say, well, then k transpose times delta p for either one of the delta p's. So I'm going to leave the subscript off from now, because we'll bring it back in a minute. Is like saying I've got minus k naught times u transpose, right, because it's k naught is a scalar, times delta px, delta py, and delta pz. And so if I wrote that out, I'd have minus k naught times u sub x, which is the component in the x direction, times delta px, plus u sub y, delta py, plus u sub z, delta pz. And so each of these, we say, well, each of these individual delta p's is a Gaussian random variable, right? Each one of these is each component is a scalar Gaussian with some variance sigma p squared. And so when I look at this, this is the weighted sum of 3 independent Gaussians, which itself will be a Gaussian with 0 mean, because they have 0 mean, and scaled by the squares, right? When I add independent Gaussians, I add their variances scaled by the squares of the scaling factors. So if I scoot this up to give myself a little more room, right, this whole thing here then, inside the sum, is itself a Gaussian where each of these is 0 mean, so their weighted sum is 0 mean. And then the new variance is ux squared sigma p squared plus uy squared sigma p squared plus uz squared sigma p squared. Right, and now I can pull the sigma p squared out in front, and I get ux squared plus uy squared plus uz squared. And I say, well, for any vector, that's just the norm of u squared. But because this is a unit vector, this part is just 1. And so, in fact, we're seeing that the variance of this weighted sum in any direction is the same as the variance of one of the components, any one of the components. And that kind of makes sense if I think in a projection sense, that if I have a kx coming in this way, hitting a sensor that was supposed to be here but then got perturbed, the only part of that perturbation that matters is the part that projects on the kx dimension. Of the 3 dimensions, I've got 3 dimensions. 2 of them are in the plane that's orthogonal to kx, right? If I sort of think about a plane orthogonal to kx here, and then I think about my perturbation away from the sensor location, one of those dimensions is orthogonal to the plane. The other 2 are lying in the plane, which has no effect on the phase. If I go back to that thing, right? If I have a projection that's orthogonal to k, it's not changing the argument in the exponent, so it's not changing the phase, so it can't affect the beam pattern. So sort of what this comes down to is, even though I'm picking these x, y, and z independently, the net variance that is projected in the direction of the wave is only one of those. So I have a sigma p squared here times k naught. So the whole thing, when I put that together, I bring all those pieces together, is that delta k transpose times delta p is itself a Gaussian. Right, so this thing here is itself a Gaussian with 0 mean, and we said, well, the thing inside was sigma p squared. Multiplying by k naught means I multiply the variance by k naught squared. And so this whole argument, k transpose times delta p, just one of those is a Gaussian with this variance. And so if I come back up here, I say, well, the difference of these 2 in the exponent is itself a Gaussian, right? If I subtract 2 Gaussians, if I multiply this kt through and then subtract them, I have 2 Gaussians. Right, so following that logic, then minus k transpose delta p sub n, which would be then plus k transpose delta p sub m. These are each individual Gaussians with this, so when I add or subtract them, I get another Gaussian, and I have, when I add or subtract 2 of them, I've doubled the variance. So this whole thing has a variance that's twice the individual thing. So that's telling me overall, by the time I'm done, if I've started with e to the minus j k transpose times delta p n, minus delta p m. That whole thing I've just shown is equal to e to the minus something, we'll call it j capital Z, where we've just shown this effective thing inside the exponent is it's still a Gaussian whose variance is 2 k naught squared sigma p squared, where sigma p squared is the variance of any one component of the xyz direction, assuming they all have the same perturbations. So we've then shown, putting all this together, that beta mn that we were looking for is equal to the expected value of a exponential of e to the minus j z, where z is itself another Gaussian. And so we're going to, you may or may not have seen this before, I'm not going to take time to derive it, but this is a well-known result that in general this will be e to the minus variance of z squared over 2. In fact, we'll probably do this in class. I'll show you this if you haven't seen it before. But for now, take my word for it that if you do this derivation, the expected value of e to the minus j z, where z is a Gaussian, will be e to the minus variance squared over 2 for the Gaussian. So in this case, it will be, the 2's cancel out here. I'll have e to the minus k naught squared sigma p squared. Okay, so I found this sort of sub-result that the beta nm, which was the expected value of the random part inside the sum, has this form here, e to the minus k naught squared sigma p squared inside. And so if I go, this is assuming, I forgot, important assumption here. This is true if, get this This is true if for the cases where m is not equal to n, where I have these two things. If these are equal, important qualifier, if m equals n, these two cancel out, they're 0, it's 1, the expected value, beta mn, is just 1. Okay, so now I can take all these and plug them all back in to this original sum up here. Right? I say I have a result for this, well, one of two results, depending on whether n equals m or not, and I can put it into this overall sum here. And so I'm going to do that on the next, I'm going to pause the video to do that on the next page so I don't run too long. But we'll see, to do that we have to break this sum into two pieces, the terms where m is not equal to n, and the terms where m and n are equal. So let me set that all up and then I'll talk you through it. Okay, so when I've collected all those terms together, we're saying the expected value of the perturbed power pattern is the sum over all m and n that are not equal to each other, to this term that looks the same as everything we saw, except beta, when m is not equal to n, has taken this form, which is k naught squared sigma p squared. And then if I think about, well, when m is equal to n, if these two are equal, I'm just getting the magnitude squared. These two are equal, so I get a 0, and this is e to the 0. And we saw this term, the beta part, was 0 when m equals n also. So I get these two weighted equally. And so I'm almost home here. I'm just saying, well, this is kind of annoying that I have this missing. Could I fix this somehow? I say, well, one of these tricks professors like to use to get to the answers, what if I add and subtract the same thing to both sides? So what if I went and added a term, or just m is equal to n again, where I have the magnitude of wm squared and this exponential term, so that I have this involved in all the terms here and I could factor it out. But if I'm going to add it here, I need to subtract it somewhere else. So I'll subtract it down here. Okay, so when I do this, I could say, well, now I can group all these together because I've got all the m not equal to n, and then I have the n terms, capital N terms, where they would be equal here. I can put all those together and say what I get for the first term is the sum over, and then when I do that, I've got this exponential that doesn't depend on m or n, so I can pull that out front. I've got an e to the minus k naught squared sigma p squared times the sum over m and n, both not equal and equal, to wn conjugate wm e to the minus j k transpose p sub n p sub m. Right? These are the nominal sensor locations. And so what I've got, and then before I forget the other term, I can bring all these together and say I'm going to get a sum over m equals n, so I could just write this as the sum over m of magnitude of wm squared, and from this one I get a 1 for each one, and from this one I get a minus e to the minus k naught squared sigma p squared. This first term up here, we circle it in blue, this whole term is the nominal beam pattern, the nominal power pattern rather. Right? If you go back and compare to where we started, this is what I thought I had. So it's saying I'm getting the nominal power pattern times this exponential plus another term, this wm, sum of wm squared, times this other constant that doesn't depend on m. So let me simplify this once more, pulling terms out front. And so this is my final result, that I have the nominal beam pattern right here, or nominal power pattern, the ideal one I thought I had, scaled by some constant that has to do with how much error I have here, right? The bigger this gets, the larger this negative exponent gets, and the more attenuation I have here. Times, if I take the sum of the magnitude squared of the wm's, that's just the magnitude of w squared, and 1 minus this exponential factor here. And so basically I've got the sum of two things, the nominal pattern, and then this thing, which is important to point out, does not depend on k. So this is sort of like a flat part that gets added everywhere. So this video's derivation is long enough. I'm going to stop here, and I'll do one more video sort of interpreting this and talking about what the result looks like.